Every automotive technician needs to understand what's inside a battery because testing, charging, and diagnosing battery problems all depend on knowing how the battery is built. Today we're going to disassemble this 3D printed battery that I've created piece by piece, and I'll explain what each component does in the real battery. We start with the battery case. In a real battery, this is made of polypropylene plastic. It's chosen because it resists sulfuric acid, handles temperature extremes, and absorbs vibrations. If we look through this front, we can see that there are 6 individual compartments. In the battery, we call these cells. 6 cells each produce 2.1 volts, and we connect those in series. We'll take a look at how they're connected here in a second. Those batteries connected in series gives us a total of 12.6 volts, the voltage of a fully charged automotive battery. On the bottom, I use 4 rubber feet to isolate the battery from vibrations. In a car, we might see something like a rubber pad or some other thing to help mitigate against vibrations. This is a plate grid. In a real battery, it's made out of a lead alloy. Here I have on this grid that I've printed, it indicates that we use a lead alloy. The lead alloy will have lead antimony, or lead calcium, or lead calcium tin. Adding an alloy or another metal to the grid helps to stiffen up the grid and make it easier for the construction of the battery. The grid has 2 jobs. It holds the active paste material in place, and it conducts electrical current to and from that material. We have 2 types of grids, positive and negative. The grid structure is similar, but the paste applied to each one is different, which is what determines its role in the battery. The paste is what actually stores and releases energy. It's called the active material. On the positive plate, the paste is lead dioxide, PbO2. In a real battery, it's actually dark brown, almost a chocolate color. On the negative side, the paste is sponge lead. It's pure lead, Pb, in a porous form. It's actually gray in color. In future lessons, we'll talk about what happens during charge and discharge to the paste that is on these plates. Between every positive and negative plate, we place a separator. This is a printed material called TPU, and it's used to electrically isolate the plates from touching each other. So the separator goes on the positive plate. I have modeled in here these large holes. On a real separator, you won't see holes this large, but this is to emphasize that this is a porous material. It is permeable, meaning that electrical ions in the electrolyte solution can actually travel through these holes. So we're electrically isolating the plates from each other, but we're ensuring that we can still use the electrolyte to interact between the positive and negative plates. In a flooded battery, separators are typically microporous polyethylene. In an AGM battery, the separator is an absorbent glass mat. Fiberglass materials that also holds the electrolyte. We'll cover this in detail in a future lesson. The electrolyte fills each cell compartment. It's actually a mixture of sulfuric acid and water, H2SO4, and H2O. The electrolyte is a chemical medium that carries ions between the positive and negative plates during charge and discharge. We actually have 6 electrolyte containers. On each of the cells, there will be a label that identifies a specific thing associated with the battery. So they're little mini lessons. We'll cover those in detail in future lessons. Now, in our model, I've used a translucent material, so you can kind of see through that. This is a liquid in a flooded. lead acid battery. If you pick up a flooded battery and tilt it, you can hear the electrolyte sloshing around inside. The liquid, as we said before, is a mixture of sulfuric acid and water, and it fills each cell compartment, completely covering the plates. These cell compartments right here are keeping the electrolyte from interacting with each cell. This is a completely sealed off area. The electrolyte that's here in cell 1 does not interact with the electrolyte here in cell 2. In an AGM battery, because of the absorbed glass mat separator, you won't hear the sloshing around of the liquid. That sloshing, once again, is only happening inside of the cell. It does not interact between cells. The plates are fully submerged in the electrolyte solution. Now we can connect the cells in series using these cell straps, sometimes referred to as intercell connectors. Each strap connects the positive plates. So if in the real battery, there'll be more than one of these positive plates. So it will connect the positive plates of this cell to the negative plates of the cell that is next to it. So we're going all the positive plates in this cell, and we're connecting them to all the negative plates in this cell. So then we would go from cell 1's positive to cell 2's negative, from cell 2's positive to cell 3's negative, from cell 3's positive to cell 4's negative, from cell 4's positive to cell 5's negative, and finally from cell 5's positive to cell 6's negative. Now we have 2.1 volts in each cell, and because these are connected in series, we're going to add those up, and that's going to add up to 12.6 volts in a fully charged battery. The terminal posts are your external connection points. The positive post is slightly larger in diameter than the negative post. That's actually by design. It physically prevents you from connecting the cables to the wrong terminal. Positive is typically marked on the case with a plus sign. You might also see it in red, or the cable that is connecting in red. It might be in white though. And the negative side is marked with a negative symbol. A lot of times that ends up being a black cable, but you want to be very careful. So look out for the indicators on the top to know what the polarity is. So the positive post connects to the positive plate in this battery on cell 6, and the negative post connects to the negative plates on cell 1. In a real battery, these are cast lead. They're not red and black like this. We did that just to make it easier to identify positive and negative, but these will both be a gray color because they are cast lead. But they do extend out of the electrolyte and the cell and then go through the top of the battery. The battery top seals everything inside. On a real battery, the cover is heat sealed or glued to the case. We use on this battery these hold down screws. They're just to be able to assemble and make sure that the top stays in position. Most batteries, you cannot remove the top without some kind of destructive measure like cutting it open. On a real battery, when we mount it in a car, we do need to use something called a hold down strap. So there'll be some type of mechanism. It might come here on the top. It might actually be mounted on the bottom and hold down the battery right here. We'll have future lessons that take a look at that, but they hold the battery into the vehicle. One of the most destructive things to a battery is the vibrations that occur as the vehicle is driving down the road. And so we want to hold it steady, and we don't want those plates to be making physical contact with each other. Every battery will have some type of ratings that you usually will find here on the top. The first one that we're going to look at is the BCI, Battery Council international. This has to do with the size of the battery and the polarity or position of the posts in the battery. So it defines the physical dimensions, the terminal locations, and the mounting configuration of the battery. The next battery rating that we care about is CCA. CCA is the cold cranking amps of the battery. Our example battery right here has 650 amps of cold cranking amps. This is the maximum current the battery can supply for 30 seconds. So the current at 30 seconds when the battery is at 0 degrees Fahrenheit or minus 18 degrees Celsius. While doing that, it's supplying 650 amps. It needs to stay above the voltage of 7.2 volts. We use this information in order to do a load test on the battery. In future lessons, we'll talk about some of the tests that we perform on a battery, but cold cranking amps is a really important one to know. We also have cranking amps, which is related to cold cranking amps. The biggest difference is the temperature. This is at 32 degrees Fahrenheit, 0 degrees Celsius. We typically don't use cranking amps during our testing, but it usually is something that you'll see on a battery. Notice that the cranking amps is a lot higher than the cold cranking amps. Amp hours is another one that we care about. So AH, this has 60 amp hours. So 60 amp hours is the amount of current the battery can supply over time before reaching 10.5 volts under a controlled discharge rate. So this is how long is the battery going to last if we do not have the capability of recharging the battery until it gets down to 10.5 volts. We also, some batteries may have something called the reserve capacity, and reserve capacity has to do with runtime of the battery under an electrical load. How long is it going to last? That's the complete anatomy of a lead acid battery. You now know every component inside: the grids, the paste, the separators, the electrolyte mixture, the cell straps, and the posts. And you also know how they come together to store and deliver electrical energy. In the next videos, we'll look at the chemistry, what actually happens at the molecular level when this battery charges and discharges.